Alright, welcome back to Math in the Bubble with your host, Mr. Daly. This is episode 10, um, and it will be our final episode because, well, I think it will be because Monday is going to be the first day back. Um, uh, Jacinda is doing an announcement at 4 p.m. apparently today, um, which will confirm that we're going back on Monday. But also, I've been sent an email that has told me not to um, put any more content out, no more new learning for this week, just so everyone can catch up for starting fresh on Monday. But I was going to provide a Zoom meeting link, so I'll put that up tomorrow, and that will run in the same time on Wednesday and Friday. So those who want to catch up, or they might want to ask me some questions about the assignment or anything. It doesn't even have to be math related. You might just want to turn up and have a talk. Then I'm just going to provide that for everyone on those days to fill in that space. But without further ado, we'll get on to working on some hyperbola problems. So with hyperbolas, I did this with the circle formula and in the exponential formula, but you can also sort of do it with hyperbolas. So hyperbolas are kind of strange. You don't use them for too much in real life, but they're interesting equations all the same. So this is a basic hyperbola that I've drawn here, and it will be y equals 4 over x. So you can think of this point here, 2 times 2, or 4 divided by 2, will give you your y coordinate. If we had x equals 4, 4 divided by 4 would be 1, so that your y coordinate ends up being 1. 2 by 2, and then up here when x is 1, 4 divided by 1, y is 4. So that's why you get that point there. Also, what's something to note about hyperbolas is that they are a mirror image there's usually a diagonal mirror going that way. So over here you also have a solution at negative 2, negative 2. So 4 divided by negative 2 would get you a y coordinate of negative 2. Yeah, so that's a basic one, and it is always centered on the origin. So it's the mirror line, if it hasn't been moved or translated, it's still basic. It will go through the origin there at a 45-degree angle. So two things to note. Another thing to note about hyperbolas is they have two asymptotes. So the axes in this case are the asymptotes. So the hyperbola never actually touches the x-axis going this way, and it never touches the y-axis going that way. So you get to infinity before you get to 0. So really there's no solution at x equals 0, because you have got a situation where you've got 4 divided by 0, and everyone knows if you put 4 divided by 0 in your calculator, you're going to get a math error, and that's just because it's always it's tending to get there, but it never actually gets there. So you can't divide by 0, therefore your hyperbola never gets there, and that's the asymptote. So when you're translating a hyperbola, you basically want to think about translating this asymptote axis. So the formula will be basically very similar to this if you're writing one. So if I just draw up another translated. If we wanted to translate the hyperbola axis to here, so now our asymptotes are going to go like this. So this is going to be x1 distance, and this will be y1 distance from here to here, giving us that x1, y1 coordinate. Then essentially it's basically you take your basic formula. So this one is y equals mx, and so in our case we've got y, and then you make instead of having a y, you've got a y minus y1, and instead of an x, you've got an x minus x1 in a bracket. So in the case of our hyperbola, our translated formula looks like this: equals, whoops, y minus y1 equals a over x minus x1. Right. So if we had this situation would be y minus 2 equals we're going to do a 4 parabola, a 4 shape factor again. Maybe yeah, we'll just keep it as 4. That'll be x minus 3. Right, so it'll look the same as our regular basic one, but it'll just be translated. So you get these points at 1, 4, 2, 2, 4, 1. And similarly on the other side. Yeah. I did that in Desmo. So the A is basically your shape factor, and that sort of determines how close your hyperbola comes in or out. So it might be more like that. What I'm going to do, I'm just going to show you on Desmos some things. So I'll just change that. Just take that off. Take the chat thing off. All right. Okay, so this is your most basic parabola, where your shape factor on the top is 1. So that's interesting to see. That's when your shape factor is 9. So what's interesting to note here is this point out here. It goes through 3, 3. And it'll also go through 0.6 at 1.5. 1.5 times 6 is 9. And then it'll go through 1, 9. another thing that's kind of interesting, if I put a negative, what happens is it just flips the axis, so it just mirrors it the other way. Now you've got your graph out that side. What else is, so this formula here is really, I might just take those off and we'll put that on. So what I've got here, I'll just drag that up a bit. This is Y1, so at the moment we've got an asymptote at, really when you're doing your hyperbolas you want to draw in your asymptotes first, right? Especially if it's a translated one. So I'll make that a dotted line. Do that to x1 as well. So we could change x1, moving it along. That's just going to drag our parabola to the side. Could be a negative 2. And by changing our y1, we're just bumping it up and down. And our shape factor, that doesn't change where our intercepts are. It's just going to make it so square numbers like 9, 16, and 25 are common ones that for hyperbolas, because there'll be a point diagonally out. So this point here, if you think about it, if we took these back to 0, well, that point is 5, 5. 5 times 5 is 25. Yeah. All right. Now, there's other ways that they. This is the probably the easiest way to draw a parabola is using this formula here, where this would be your shape factor A. But if you know how to draw it from 0, 0 origin, then it's as simple as just bumping it left or right using x1 or y1. And of course you can bring that generally, this is actually a good thing you can do with this. What I'm going to do, I'm just going to put this y1 on the other side. So we'll delete that, and we will have plus y1. So this is probably how the formula might be on your formula sheet, because everything is y equals this, this, and this. Yeah, so that didn't actually change our hyperbola. If we have, say, y is 5, it's bumped it up by 5. So that's why you get y as a plus and x1 is a minus. Really it's a minus, but it should be over there with the y. Okay, I think a good idea for us to do now would just be to draw a basic one just from an equation, and draw one from an equation. Alright. Okay, let's draw this one. Y minus 3 equals 16 over x plus 2. So generally you're not going to be given the minus 3 on this side. It will actually be a plus 3 on this side, but you've got to know that, well, that's going to bump up our y asymptote that way. So that is a result of that plus 3. This will be a negative 2 asymptote. So that will be there. Okay, now we can just sort of think of this as just another set of axes. So but also what you can do is sub in x points just to see what happens. So x equal, so we'll make up a little table. X or y, let's just count from 0, see how we go. So in this equation, if x is 0, what will y be? 16 divided by 2, because x is 0, is 8, plus 3 is 11. Am I right? Yeah. 11. So that'll give us a 0.011 on our x's. So at this point, the hyperbola crosses. So you can do this with any graph, just subbing in x values to see what you come up with. So 16, oh, that's going to divide by 3, which isn't going to be nice. Let's just not do 1. Let's try 2. 16 divided by 4 plus 3 will be 7. It's another. So that's going to get us x equals 2, y equals 7. Will get us that point. And what you can see is that if we draw a diagonal line, that's the point where the hyperbola starts going back on itself again. So this point would have an equal and opposite point somewhere along the right line. We just got to think, where's another place where 16 is going to divide by 2 evenly? Well, it would divide at x equals 6, so let's put that in. 6 plus 2 is 8. 16 divided by 8 is 2. Plus 3 would be 5. So we would have one coordinate at there's x equals 6, and there's x equals 5. But once you know how the formula works, then you just need to know, oh, this just moves my x asymptote, this moves my y asymptote. So if you understand how that works, then you'll notice that you can see they are tending to these asymptotes. So if we had a mirror image over the other side, it would be 4 this way 4 this way. So you're going to have a point there, and you're going to have a point at 2 and 8. So there's 8, there's 2, 8, 2. So I'm just counting over. So there's 4, there's 8, there's 2. So you'll get alright. Now, another problem you are likely to get, maybe not in this graph assignment, but later in graphs, is the intersection of a line with the hyperbola. So to do the intersection, the hyperbola, sorry I said parabola, and a line, this would be probably a merit type question. So we'll just use this equation, and I'll just make up a line equation. So we've got y equals, let's go through point 2, and we'll go up. We'll have a quite shallow gradient. We'll go let's go 2/5. Rise 2, run 5, 2x plus 2. So essentially this line is going to go up 2, across 5, up 2, across 5. So essentially it's going to cross through these points which aren't on grid points. So how do we figure those out? Well, generally when you're trying to find intersection points, you just set the two equations equal to one another. So this is our equation 1, equation 2, so we're going to go 1 equals 2, so we're going to get 16 over x plus 2, 2 equal, God, 2/5 x plus 2. Alright, so when you're doing algebra, you generally want to isolate this fractiony part before you do any other algebra steps, because it's just this is gonna mess with it. So we want to move that plus 3 to the other side to become a minus 3. So your next step would become 16 over x plus 2 equals 2/5 x minus 1. So just minus 1 from both sides. Because usually you don't have a bracket around this term at the bottom, but I would put a bracket around it because you've got to deal with it as 1. So what we want to do is we're going to multiply this to the other side. So if you think about it, this, if it's multiplied to the other side, it's going to multiply both things. So we should put a bracket around these as well. So you're going to be left with 16 equals 2/5 x minus 1 x plus 2. And right away you can see we're going to get a quadratic. So we're going to need to use our quadratic formula. to solve this. So let's expand this and put the 16 on the other side, because remember we want our equation to equal 0. Oh, I might just leave that for now. We'll just expand first. So expand 2/5 x times x makes 2/5 x squared. 2/5 times 2 is going to be 4/5 x. Negative 1 times x, negative x. Negative 1 times negative 2 times positive 2 makes negative 2. These terms here are just single x terms, so they can be put together. 4/5 x minus x would be negative 1/5 x. And remember we got our 16 over here, so we want that to be over here with that negative 2. So we're going to end up with negative 18. And there's no other x squared terms, so we'll just leave that as it is. And that all equals 0. Once you've got it equal to 0, now you can use this in your quadratic formula, because you can peel off your coefficients. 2/5 is A. B is going to be negative 1/5. C is going to be negative 18. Alright, I'm just going to... you guys know the formula. Quadratic formula into... Quadratic formula is minus b plus or minus the square root of b squared over 4 AC. So we're going to have negative 1/5 plus or minus the square root of negative 1/5 squared minus 4 times 2/5 times negative 18. That was lucky. So we've got two negatives will cancel out, so really this is going to be a plus here. And oh yeah, this is all divided by 2a. So 2 times a just going to bring that back up as front top. So more simply, that's going to be 1/5 plus or minus 1 over 25 plus 4 times 18 times 2 divided by 5. Maybe we'll just add 1/5 to that. 1/25 plus 1 divided by 25. So really this is 1/5 plus or minus the square root of 28.84 divided by 4/5. Or let's replace these fifths with decimals. So 4/5 is going to be 0.8. 1/5 is going to be 0.2. So that's a bit easier to put into your calculator. Alright, 0.2 plus 28.84. Oh, we wanted to put brackets around all of this. So that whole top thing is divided by 0.8. .963, and if I change that to a minus, we'll get our other solution. Negative 6.462, oh, 63. Are those sound feasible? Oh, actually, they are pretty accurate. So if I go back to my graph, we have a negative 6.643 corresponding to that one, and over here we've got very close to 7, 6.963. So it does help to draw the graph because you can see how close you were. And of course I might go, we'll work out the y value for that. So to do that, don't use the hyperbola equation, although you could. Let's use the hyperbola equation just for the sake of it. It's not too difficult, really. So x1 equals that, x2 equals that. Y1 is going to equal 16 over substituting in 6.963 plus 2 plus 3. 16 divided by 6.963 plus 2 plus 3. Y1 equals 4.785. Does that sound feasible back to here? Yeah, because that was very close to 5, just a little bit lower than 5. That makes sense. And our Y2, if we used our, well, we could use the hyperbola. Let's use the line to see if we get the same thing. 2/5 of our x2, negative 6.63, then we're going to add 2. It's getting very squished in here. So on our calculator, 2/5 times, oops, we don't want that, negative 6.463 plus 2. So negative 0.5852, which is about right. Yeah, just slightly negative, not quite -1. That would be -1 there. So just a low. Okay, that's hyperbolas. Well, it's not actually. There's what I noticed on the. I'll just open up Schoology. So this one here is a hyperbola. So what you could do is sort of type that in and see what's going on. It's just, you could imagine this is like this regular one that's just been sort of rearranged. They've done some tricky algebra with it, to make it look like that. But you can sort of figure out where the asymptote should be on this one. But, you know, if in doubt, go to Desmos. So I'm just going to write that down on a page so I can type it into Desmos. Just turn off all of these. So, yeah, you get given occasionally these funny ones that look like 2x minus. So all of that divided by x plus 2. Okay, so let's zoom in on what's going on here. So what it appears is that there is an asymptote at x equals 2. If we squished up our graph, then our asymptote is at 2. Now you might think, why is that for this particular type of graph? Well, think about x going to infinity. If x is going to infinity, then the minus 4 doesn't really matter anymore. And also, this plus 2 doesn't really matter anymore. So, really what we have is 2 times infinity divided by infinity. So, as x goes to infinity, y tends to get closer and closer to 2. So it's tending towards 2 as x goes to infinity. So these are other ways. So the other thing is, if what makes y go to infinity? Well, that happens when this bottom term is very close to 0. So if I go x equals minus 2, that'll give us an asymptote that our graph tends to. It never actually gets there. If you zoom in on it, it'll never actually get there, even though it's very, very close. And that's because this bottom part of the fraction can never be 0. So it's always getting closer and closer. The closer it gets, the more infinity y will get. So you can use those two things. So what's happening as x is going to infinity, and then what's happening as this bracket, what's under the fraction, is heading to 0, and you can use that to find your asymptotes. Let's just have a look at some other values. So this value here, where it crosses, that's something that you could calculate. So when y is 0, what would x have to be? Well, you could solve that with a bit of algebra. So if y is 0, then this bottom term, if you multiply it to the other side, it's just going to get cancelled out. So you're going to be left with 0 equals the top term, 2x minus 4, which means that, you know, x needs to be 2 for this to work. And I don't think there'll be any other solutions for that. Yeah. Okay. I can't think of anything more to say on hyperbolas. But in general, if you've got something that looks like this, type it into Desmos if you have no idea what it's going to look like. But you can always just sub in x equals 0, what does y equal, x equals 2, what does y equal, and draw your own graph from that. So that's, you can always fall back on that. Okay. Yeah. So we might just end it there. This is the last Math in the Bubble episode, which is very sad. Thank you, Helen, Jack, and Yana for always tuning in. You know, there's 20 other students in the class who aren't as dedicated as you, and it's great. You really got me through all of this. If no one turned up, it wouldn't have been worth it. So thank you for that. But remember to go watch the news now, because Jacinda has got a very important announcement to make that could affect you. But yeah, I'll post this episode tomorrow and just yeah, how we're going to do the Zoom meetings and just explain what I think we should do from here. Other than that, thank you for tuning in again.